Okay, so now we are considering a circuit with a capacitor of capacitance C and with an inductor with inductance L, and we want to find how much energy is stored in the circuit. So let's think of the work that we have to do to charge the capacitor. So we're going to pull a tiny little bit of charge and put it on these plates and imagine a tiny amount of work to do that, which is just, from the definition of work, F dot dl or F dot dr. Right, but we're talking about the electric force. We have to work against the electric force. So we'll replace F with the electric force, and then write this in terms of voltage, or electric potential difference, dV. And from the definition of capacitance, we can get an expression in terms of little bits of charge. Right? These two things are not independent of each other, and so our little bit of work is Q over C in dQ, and that's what we want to integrate, so that the total work, and therefore the energy that's stored, going to be the integral of these little bits of work. To take little bits of charged particle and put them on the capacitor plates. Well, we're going to integrate this quantity from zero charge to some total amount of charge, Q, on the plates. And this gives us Q squared over 2, which we evaluate from 0 to capital Q. And that, of course, gives us capital Q squared over 2C. So that's an expression for the energy stored on the capacitor in terms of charge and capacitance. Of course, we could rewrite this in terms of capacitance and voltage. So that work could be written in terms of capacitance and voltage, just from the fact that Q, right, is C times V, right? The maximum charge that we put on the capacitor, Q, is related to the maximum voltage via the definition of capacitance. So that's the energy in the capacitor. Now let's think of the energy stored in the inductor. Well, here we're thinking of getting a current to flow through the inductor, and we have to work against the EMF, right? So we know that there's an EMF. That's an energy per unit charge, and so the minus sign, we're working against that in the same way that we had to work against the electric field to put charges on the capacitor plate. So we want to multiply this by charge, right? So we want a notion of work minus Q times epsilon, but we want this in terms of current, so it's not work, it's the rate of work that we end up getting, which is, we divide that by T, we get minus current times epsilon. So that's dW by dt, and so in terms of minus epsilon is L di by dt. And so we have a dW, which looks like L I di. And so the work we have to do to get a current flowing is the integral of this from 0 to some current I, capital I, of I in di. and that gives us Li squared over 2. So the energy that's stored in a capacitor depends on how much charge we have, and the energy stored in the inductor depends. So the energy stored in the capacitor depends on the amount of charge stored in the capacitor and the capacitance, and the energy stored in the inductor depends on the inductance and the amount of current that's there at that time. And these two things added up together will give us the total energy in the LC circuit, and we'll see that the energy in the LC circuit doesn't exit the circuit, that it flows from the magnetic field to the electric field, or from the capacitor to the inductor and vice versa, in the same way that the energy goes from potential to kinetic in a simple harmonic oscillator.